Hi all, today we are going to discuss force due to magnetic fields. So, there are at least three ways in which the force due to magnetic field can be experienced. First can be due to a moving charged particle in a magnetic field, and the second one on a current element in the external B field or between two current carrying elements. So, today we are going to discuss about the first two cases, that is due to the moving charged particle kept in a magnetic field, and the second one on a current carrying element which is kept in an external magnetic field and some numerical. So, tomorrow's class we will discuss about what will be the magnetic force between two current carrying elements, if their elements are small as well as long two current carrying conductors. So, let us discuss the force on a charged particle, the force on charged particle. So, now considering the force on a charged particle, there are two things we have seen. So, let us take for example, there is some electric field. So, there is some electric field, let us assume the electric field is uniform throughout the area. So, if a charge is kept in this electric field, we know that it will experience as a force in the direction of the electric field. This force exerted by the electric field on the charge, whether charge is stationary or moving, this will be given by the charge multiplied by the electric field Q into E. This you have seen in electrostatics. Similarly, it is observed practically that, let us assume I am taking a magnetic field. Inside this magnetic field, let us assume the uniform magnetic flux density is there B. So, inside a magnetic field, if you keep some charge Q, the force experienced by this will be equal to 0, and force will be exerted on this charge only if the charge is in motion. That means, let us take for example, this charge is moving with some velocity u in some particular direction. So, it is observed practically or experimentally that only when the charge is in motion, then only force will be exerted on this charge, otherwise the force will be equal to 0, and this force is given by force due to the magnetic field on a moving charge. The charge is moving with a velocity of u will be Q into U cross B. This is what is observed practically, that it depends on this one. Or we can tell the net force exerted with the combination of both electric and magnetic field will be the sum of, or the vector sum of, the force due to electric field and the force due to magnetic field, or I can tell my force F is equal to Q into E plus U cross B. This is what we get. So, if the electric field is there, then E will be there, otherwise E will not be there. Only if magnetic field is there, U will be there, otherwise it will not be there. Otherwise, the force equation can be written in a generalized way like this. So, this is called as Lorentz force equation. So, this relates the mechanical force to electrical force. This relates mechanical force to electrical force. This is very much useful in analyzing the force exerted or the working principle of electrical machines. So, now this force can be written as mass into acceleration. We know acceleration is nothing but rate of change of velocity. So, m into du by dt, where this m is the mass of this charged particle on which we want to calculate these things. So, this will be equal to Q into E plus U cross B. So, this way we have to calculate the force. So, force is a vector. Now, let us see what will be the force on current element. Current element means, so inside a magnetic field, a element is there or a current carrying conductor is there. What will be the force exerted on this? Because it is a current carrying element, so the current is moving or the charges are moving with respect to time. That means there is a velocity of the charged particles. So, automatically force can be exerted. So, we have seen in our lecture number 35, where we have seen about the current and current density. So, one thing I want to tell you, I am writing on a glass screen, so the handwriting does not come properly. So, I have provided the complete handwritten material in the description of this video. You can please download the handwritten material from there. Here you try to understand the concept, because my major concern is to teach you the concepts. Remaining required material you can please refer from that handwritten material. So, we have studied in this lecture number 35 that J is equal to volume charge density, because current density is equal to volume charge density multiplied by the velocity of the charged particles. So, let us take it as equation number 1. So, and we have also seen in this beginning of this chapter that current element can be defined as IDL, or it can be defined by KDS, or it can be defined by JDV. So, let us take it as equation number 2. So, now combining these two equations, I can tell that this IDL is equal to, because IDL I can write as rho v into u dot dV, because ideal is equal to j dV. So instead of j, I am substituting this one. So that is what I have done, rho v into u dot dV, or this I can rearrange because u dot dV, because dot product is interchangeable or it is commutative. So this I can write as rho v into dV dot u. So rho v dV will be nothing but the charge only. So it is a differential charge because you are taking differential volume. So dq dot u. Let us take this as equation number 9. And we know that differential force that is exerted, we have seen in our previous section. So this will be equal to dq into u cross b. This is what we have seen. Or this dq into u, we have just proved here, this dq into u is nothing but ideal only. Refer here, this L, dl is a vector. So this will become idl cross b. This is what is obtained from this one. So we can tell the magnetic force that is exerted, that will be equal to line integral of idl cross b. I am just taking the integration of this one, that gives my magnetic force. Or this I can written in terms of surface charge density, that will be equal to kds cross b, or this I can write as volume charge density of j dV cross b, because whatever way you take, so that way you can take this one. Getting it? So now here you can observe from this equation dFm is equal to idl cross b. From this I can define my magnetic flux density. Magnetic flux density is nothing but force on unit current element, or force per unit current element will be equal to magnetic flux density. This is another definition of the magnetic flux density. Let us assume the conductor is straight. When the conductor is straight, whatever you do the line integration, that will be nothing but the length of the conductor itself. So if you are taking a straight conductor, so this can be written as Fm will be equal to I into, let us assume L is the length of the conductor, this will become L cross B. Or this cross product of two vectors is nothing but the product of the vectors magnitudes multiplied by the sine of the angle between them. So I can write that the force that is experienced will be equal to B into I into L into sin theta, where there is the magnitude, please remember this one. So this theta is the angle between I and B, current and the flux density vector. So based on what is the angle between them, accordingly the force will be exerted on the current carrying element. So let us take one example so that this will be much more clear to you. I am taking one example. Find the total force on a loop of wire in the z is equal to 0 plane carrying 2 milliamperes in the field of an infinite filament on the y-axis as shown in figure. So that figure is given here. It is given that there is a z-axis, there is y-axis, there is x-axis, and the loop is given here. There is some current loop. That current loop is starting from here. That current loop is lying like this. This is the current loop. This current loop is also mentioned. It is carrying a current of 2 milliamperes. It is passing from 1, 0, 0. This is 3, 0, 0, and this point they have mentioned as 1, 2, 0. So this one we can calculate accordingly. So, and one more thing, there is one more current carrying conductor of infinite length that is carrying a current of 15 amperes, and the medium that is there, that they have mentioned as free space. This is what is mentioned. So I want to find what is the force exerted on this current loop. So what is the force exerted on this due to current passing through infinitely long current carrying conductor. Let us see how to calculate this one. So to calculate this one, the force produced, let us see what is the field intensity due to this long current carrying conductor. We have already derived this one in our previous lecture. This will be equal to I by 2 pi x in the direction of Az. I by 2 pi x in the direction of Az, because this is the value of the h. So how to find the h? Whenever you are, if you hold your right hand in such a way, if your thumb is indicating the direction of your current, then your curled finger indicates the direction of magnetic field intensity. So that indicates the direction of the magnetic field intensity. That is what we have seen. So that magnetic field intensity due to long filamentary conductor, this will be along the z direction only, or the tangential component, that will be equal to I by 2 pi x in the direction of Az. So this I can write as 15 divided by 2 pi x in the direction of Az. This is in amperes per meter. Fine. So now we can calculate the flux density from this, because you will get doubt why Az, because I want to find because of this conductor at this point on the conductor surface, because conductor is lying on the xy plane or z is equal to 0 plane. At this plane, if you calculate this one, let us take for example, if I take a conductor, this conductor, let us assume the current is going inwards. So in that case, so the magnetic field intensity, if you apply your right hand rule, because thumb is indicating inside, you will get your curled fingers that indicating the direction of the magnetic field intensity. So if you are keeping it horizontal, you will see at this point what is coming, it is tangentially upwards. So this is along the z direction only. So that's why I have written Az direction. Please don't confuse here. So B I can write as B is equal to mu naught into h, because it is in free space. So this will be equal to 4 pi into 10 to the power of minus 7 into h. So h we have obtained above. So this I can write as 4 pi into 10 to the power of minus 7 into 15 divided by 2 pi x in the direction of Az. This will be in Tesla, or this value of B, if you calculate, you will get it as 3 into 10 to the power of minus 6 divided by x in the direction of Az Tesla. So now I want to calculate the force. So force will be equal to, force I have just derived, the force can be written as closed integration of IdL cross B, or this I can write in another way, this I can write as minus integration of B cross dl, and this I is constant I can take out. Why this minus sign is there? Because A cross B is equal to minus B cross A. I can write in that form, I am using that formula here. So this I can write as minus 2 into 10 to the power of minus 3, that is the current, multiplied by 3 into 10 to the power of minus 6 into, I have to do the integration of B cross. So different loops I am applying. First one is I am varying from x is equal to 1 to 3. This is Az by x. This I will cross product with the differential length, this is along dx, x direction. So dx in the x direction. Then second integration is from y is equal to 0 to 2. That means it is along the y direction. This will be Az divided by 3, because x is equal to fixed here, it is 3 multiplied by dy in the direction of ay. This is the cross product. So now the third one will be integration from x is equal to 3 to 1. This will be Az divided by x. This will be cross product with dx in the direction of ax. Differential length is dx only. While taking the integration, I am taking from 3 to 1. That's why it is already taken care, the current is in opposite direction. Please unnecessary, don't confuse, don't keep here minus dx, because answer will go. If you are keeping minus dx, then integration will be from 1 to 3. Please remember this one. Many people do this mistake in the exams. So this will be y is equal to 2 to 0. This will be equal to Az divided by the value of x is equal to 1 here. This cross product with dy in the direction of y. This is what is there. So this I am just substituting the values. This will become minus 6 into 10 to the power of minus 9 into ln of x. The limits are from 1 to 3. This will be in the direction of ay, plus 1 by 3 into y. The limits are from 0 to 2. This is in the direction of minus ax, plus ln of x. The limits are from 3 to 1. This will be in the direction of ay, plus y. The limits are from 2 to 0. This will be in the direction of ax. So why this came? Because we know that whenever you are taking, this will be ax cross ay will be equal to az. So in this order it will go. If you go from ay cross ax, this will be equal to minus az, because you have to go in the sequential order. That means ax, ay and az. If you go in this order, it will be positive, otherwise it will be negative. We have discussed in the basics. That's why these came, cross product of the things. So this, if I am simplifying, this will become minus 8 into in the direction of ax nano newtons. So you can see here the net force is in the minus ax direction, having 8 nano newtons. That is the force exerted on this current carrying element. I hope that how to calculate the force due to current carrying element and what is the force on the charged particle is clear to you. If you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you very much.